Hello, everyone. We're working through statistical methods for rates and proportions, Chapter 8, Randomized Control Studies, Section 8.2, the two-period crossover design. So the crossover design happens when each patient serves as his or her own control. And we do this when we don't have a natural control group, or sometimes it's just not possible to have a control group. What happens is that you select a random sample of your patients to go in the order A and then B. So they take treatment A, there's often a washout period, and then they go to treatment B. And then the other half of your patients are going to start with treatment B, have a washout period, and then go to treatment A. So each patient is serving as their own control. All right, so we are going to define two different tables. This is given in table 8.2, where we think about the response to A as being good or bad, and the response to B being good or poor. And we do the same thing for the patients who are ordered B to A. So the table that's A to B is going to be defined with values of N. And the table that's the order B to A is going to be defined by the values of M, M as in Mary. Okay, so here we have an example where we set up our table with the A to B patients. And when we do that, we see that for the patients who were ordered A to B, they were either a good response for A or a poor response to A. And then a good response to B and a poor response to B. And when you think about this, if a patient responds good to both treatments, their information doesn't help you very much. And if they respond poorly to both treatments, their information doesn't help you. But what does help you is the people who respond good to one treatment, but not to the other. So really these discordant pairs on the off diagonal are going to give us the most information about the patients who are ordered A to B. We can do the same thing with the B to A patients, and now we're using the value of M to define them. Okay, so for our B to A patients, they either respond good to A or poor to A, good to B or poor to B. And once again, if they respond well to both, their information isn't helping you decide which treatment is better than the other. Similarly, if they respond poorly to both, their information is not giving you a lot about is A better or is B better. But who does give you information is the people who are responding good to A but poor to B, right? This discordant pair. And also the people who are responding good to B but poor to A, those people are also giving you information if you're trying to decide is A better or is B better. All right, so table 8.3 on page 164 of our text is looking at the equal treatment effectiveness. So if we set this up, we're really asking, was our first treatment better or was our second treatment better? And in the rows, we have our ordering. So here, for the patients who went A to B, how many of them was the first treatment better, right? And for B to A, how many was the first treatment better? So in this case, we're also looking to find out, is it the actual treatment or is it the order in which you received the treatment? Because if we gave everyone drug A first or treatment A first, then they responded well. The question really becomes, are they responding to the treatment or are they responding to the first thing they got? So it's always something that you want to check. All right, that's why we gave half the patients the opposite ordering. All right, so we can get the value of N and the value of M. Okay, so the first row, if I use the apply function, remember I'm getting for the table T, I'm summing up the rows. The first value is going to give me the value of N. The second value will give me the value of M. And I can also get the column sum. Okay, so if we look at proportion 1, we can take n12 over n, and we notice that that's 0.75. So for the patients who were ordered AB, there's 20 patients total. 15 of them responded well, so the proportion is 0.75. For the proportion 2, we're thinking about the patients who were ordered B to A, right? So our total number of patients there is 15. And then we have 5 out of 15 patients, giving us 33%. All right, so we can get Q1 and Q2 by taking the complement, 1 minus P1 and 1 minus P2 respectively. We can calculate P bar as the average success rate, right, for all the patients combined, assuming that the true proportions are equal. We get P bar to be 0.57. We can get Q bar as 1 minus P bar, and then we can use the traditional difference in proportions. Here we take the difference of P2 and P1, we subtract off the continuity correction, and then we divide by the standard error. So we get our test statistic, which is 2.11, and our p-value of a two-sided test would be 0.034. So when we look at this, we see that the effects of treatments A and B are significantly different. And what we've done here is we've been able to test the difference in the proportions while considering whether or not order matters and allowing each patient to serve as their own control. So I hope you learned something in this video, and I'll see you next time.